building at that level. So floor plan area. So it is very simple. It can be done by elementary school students. But it is very good to get a sense of this index, which can be expressed in a percentage. And percentage meaning 1%, 2%, 3%. So it is what is the percentage of walls in each direction relative to the plan area. This concept has been used extensively in countries like in Latin American countries. It is also included in Eurocode 8, for example, in section on masonry. So that is important to know. But I'm not going to cover the way that is used in the other codes, but I will explain how we can use it in India. And this derivation or a part of it is included in chapter 7 of the Confined Masonry book. Derivation is not included in the code, but only the concept. So here I'm going to just to show you a little bit of examples. This is an example actually on reinforced concrete wall structures, but there are quite a few papers related to confined masonry as well in Chile and this wall index. So I like this paper, and I included on the left-hand side are some values for Chile for confined masonry, and on the right-hand side are the values. The diagram is for concrete shear walls. So in Chile they use this method to determine to get a sense of the percentage or index both for masonry and for concrete buildings. For confined masonry, for example, in the building that was in the very strong earthquake that happened in 1985. I mentioned the 2010 earthquake, but there was a strong earthquake on 1985. I believe it was magnitude 7.8. They found that in that earthquake, after assessing the buildings, after visiting the buildings that had a wall density index or wall index of let's say 1.15% or more, had a very light damage. The buildings that had between 0.85 to 1.15% in the same way, determined the same way as I showed you on the first slide, had moderate damage. And anyways, the buildings that had less than 0.5% survived heavy damage. So that was for confined masonry buildings. And similarly, in Chile, for example, they did similar studies after every earthquake, and every 10 years they have earthquake of magnitude 6. So in that case, in Chile, they have lots of data on this wall index. They also use it for reinforced concrete walls, and you can see here the percentages are different, a bit higher. So these are all data in Chile. The blue points are data for concrete shear wall, reinforced concrete shear wall buildings. In Chile, they don't use frames, reinforced concrete frames almost at all. They use either confined masonry as far as masonry is concerned, or in concrete, they use concrete shear wall buildings. So the walls are the main, shear walls are the main elements of lateral load resistance. And then you can see percentage of wall area relative to the floor area. You can see it ranges from 1% to all the way to 8%, depending on the building. And they show the trend through the years, how this percentage changed. So just to get a sense, and that is all at the first story level. So they wanted to show that in some cases they got lower percentages, that they're now around 3%, whereas earlier 10, 20 years ago, like in 1995, they were like many buildings had 5% or 4%. So in any case, the left, the values, what is relevant for us studying confined masonry are these values that I've shown. So you can see value of 1 is critical, or 1.2, let's say, or higher means no damage, and less than 0.5 means heavy damage. So let's see how this can be determined numerically in a rational way. We cannot say just this is from Chile and therefore it will apply to India. Because why? Because these values are determined on actual strengths of masonry, and they are different in Chile than from India. And so that is the reason, actually, no other reasons for shortage of comparison between countries. So the whole concept of the wall index is coming from the comparison of seismic limit states analysis. As I mentioned in the previous lecture, we are focusing here in all lectures, and any calculations will be based on limit states analysis. So ultimate limit states or design. So we are here comparing in this equation. VR means shear seismic capacity of the shear capacity of the building, which is based on the materials used, which is based on the number, amount of walls, thicknesses of walls, and so on. We will see how to determine that. And on the right-hand side is seismic force for the entire building. So it is not for one wall. We are talking at the base of the building. So this is the capacity at the base of the building, and this is the force at the base of the building. How do we determine this force at the base of the building? What do you think in India? Can somebody answer this question? So this force is determined, I think everybody's muted, maybe that's why not. So this force is determined from IS 1893. Today in the afternoon, you will have a review of IS 1893 procedure. So this is a base shear force by IS 1983. So, and then why is this multiplier 1.5? Well, that is a load factor. You remember we talked about load factor of dead load plus earthquake is 1.5 dead load or 0.9 dead load plus 1.5 earthquake load. So we are here talking about, in both cases, we are talking about ultimate situation. On the left-hand side is ultimate strength of the whole building in one direction for the effect of earthquake loading. On the right-hand side is the applied loading due to that earthquake. This is mentioned here. So we call this seismic forces, we call it popularly known as seismic demand. But in reality, it is seismic shear force. So in technical literature, this is known as seismic demand. But it is seismic shear force at the story level, which in this case, it is at the base of the building at just above the foundation. So so how to determine these forces? As you know, and you will review in the afternoon, seismic forces are determined, at the base, and then they're distributed along the height. So in this case, we could apply this to any level of the building, but for our interest is just the base level. But this just shows that the force, story force at any level in one direction of the earthquake is equal to the sum of forces above, seismic forces above that level, isn't it so? So that is clear. So if that level is at the base, then that means that all forces are taken into account. In fact, we don't then need to even divide into different forces. We just calculate the force at the base. So now the next thing is at that level. Let's imagine this is a ground floor of a very simple building with 3 walls. And we have 3 seismic force acting in this vertical direction, that is that force Vx. And we have these 3 walls, 1, 2, 1J and N, let's call them that way, IJ and N, okay. So in this case, we consider the walls for this purpose. The question is, how do we determine this seismic force which is applied by the earthquake to these different walls? Because the design process starts from calculating that force, then finding out what are the forces in the individual walls in case of masonry structure, and then checking whether that force in the wall, which is shear, and then it could be bending moment also as a result of it, but let's say we are limiting here to shear forces, whether it is adequate, whether the force exceeds the capacity of that wall to resist shear. So that is what we are checking here. And please note that in this case, we are considering rigid diaphragm approach, a rigid diaphragm assumption, so that you can see that this, under this force Vx, this line AB, which is the diaphragm, moves to A prime, B prime, and the displacement dx is the same at both sides. So it is like a table. I like to explain that as a table. Imagine that you are moving a table. So if you move a table, if you push it equally in the middle, it will move by the same amount. Each point on the other will move by the same distance. So in any case, in order to find the forces in the walls, these three walls, we need to model them as horizontal springs with the stiffness K. So K is the wall stiffness for shear. We assume in this model that only shear, that the predominant action is shear, that the wall shear forces are resisted and that the shear resistance of the walls need to be adequate. And one of the characteristics of the walls based on which we distribute the forces in buildings with rigid diaphragms is their stiffness. So you know that, and it is mentioned here in the text, force distribution to the walls proportional to stiffness, rigid diaphragm assumption. So if in this case we have this wall I on the left side, which is the longest, the walls are the same thickness, but the one is the longest. This one will have the largest stiffness and will attract the largest, take the largest portion of this force Vx. Wall in the middle, J, will be something maybe smallest, but anyways, we will have to, our goal is to find force in each and every wall, and that is the wall shear demand. So wall shear force or wall shear demand is the demand or force due to seismic loading. So let's call this Vjx because the wall is called Jx and V is the seismic force. So it is not the stress, it is the force. Now, this is, we are coming to equations. Top equation is telling us how do we determine the force in the wall. Force in the wall is equal to the stiffness of the wall, which is the characteristic of the wall. It has nothing to do with applied loading, and the displacement. We already talked about the displacement. The displacement is equal. Or the other way of showing it, because we said that the force is proportional to the stiffness, it will be, and we will use this second form, is that it is equal to the stiffness of that wall divided by the sum of stiffnesses of all walls in that direction times the total force. So if let's say this wall is this wall is 50% of the total stiffness of all walls, then half of the seismic force at the base of the building will go into that wall. Then how do we determine the stiffness of the wall? We say it is a fixed property. The stiffness of the wall for shear is equal to the shear modulus. Remember shear modulus from the last lecture, 0.2e, times area, cross-sectional area of that wall, meaning in horizontal direction, meaning length to thickness, divided by the story height for that wall, let's say 3 meters or whatever it is. So in this case, area could be 5 meter long times 23 centimeter thick, so that is for a brick masonry wall. And so if we have the same height and all bricks, all walls are made of the same masonry, now this first equation where we have stiffness proportion will convert into proportion of areas, so that we can find the force in any wall as a fraction of the area in that wall relative to the area of all walls in that same direction. So this is a simplified already equation, and this is possible only because we are ignoring a flexural stiffness of the wall, because in this equation for K, we would have one more term which would relate to flexure. However, since confined masonry buildings are low-rise buildings, and the way dimensions of the walls are exist or are likely to happen, we expect to have predominant shear effect, so therefore we are ignoring flexural stiffness in this calculation. So it says here stiffness of individual walls is proportional to its cross-sectional area. Then story shear capacity or resistance. Now that was all about applied forces. Now we need to find what is on the other side. So remember the other side of equation we are going to the other side of equation. We cover this part of equation, the right-hand side, and found how do we determine forces in the wall due to seismic loading. On the left-hand side, we are now looking into VR, which is the shear, the stiff resistance of the wall at that same level. And so we are here. So resistance of all walls in one direction is equal to the sum of stiff resistances of all walls of each individual wall in that direction. So now the question is, how do we find the resistance of one individual wall? Let's say with the specific length 5 meters and the thickness 23 centimeters or whatever. And so we are going to use the shear stress equation. So you know that the average shear stress for the force that is applied, let's say horizontally, parallel with this, you look at this cross-sectional area, length and thickness. If you have a force that is acting along the length, that is a shear force, the average stress due to that force would be equal to force divided by this area, length to thickness. Therefore, if we are now, since we are looking in the limit states design approach, we are not interested in stresses, we are interested in forces. So the force is equal to the stress times area. Now the stress, the maximum stress that this masonry wall can take is the basic shear strength. So that is that VR. You remember we were talking about VM. Actually, that should be VM instead of VR. In this case, VR could be due to masonry, could be due to steel, if there is steel. So in this equation, in fact, we should have VM and not, maybe you can correct that, VM and not VR because of the nature of unreinforced masonry. And then it is divided by gamma M to get the allowable, the reduced value of stress. So in this case, we will need to divide it by 2 in order to get this value. So masonry shear resistance or basic masonry shear strength is equal to Vm, which is equal to 0.16 square root of F prime M or Fm as it is mentioned in the code, but not more than 0.6 megapascals. So we were talking that this value is actually based on the testing by CADAM and some recommendations in according to ERI guide is on the order of 0.3 megapascals. If you divide that by 2, which is the value, then we are getting 0.15 megapascals roughly. So you're multiplying 0.15 times this cross-sectional area and you will get a shear resistance of this wall. So that is how it is used for this calculation. You will see that on Thursday, first lecture, I believe, is the one on the detailed design of the wall. So you will see that the detailed equation according to the CM code for India is a bit more detailed. It's not that simple, but this is again simplified method, therefore simplified equation. So if you want to do yourself, unfortunately I cannot write this. I'm sorry about that. In fact, maybe what I can do is what some people do, I can write it by creating a new slide. So let me see if I can do that. So, and then I can create a layout like this. So here we can say that our VR, maybe you can annotate on your own lectures, is equal to approximately 0.15 MPa times area. Why 0.15? We said that assume that Vm is equal to 0.3. We were saying 0.3 MPa, and gamma for masonry is equal to I have to use this. I'm really used to annotate. Maybe later on we can check if I can use my tablet, but I'm using it without problems for Zoom, but maybe there is a problem. So we have gamma m is 20, and we said that these two values are divided. That's why an area, let's say wall length for the purpose of calculation is, we can easily calculate it. In fact, I want to just get a sense. We have, let's say, length is equal to 5 meters and the thickness is equal to 0.23 centimeters. So then the area is 5 times 23. So it is 1.15 meters, or maybe we can express it in, okay, so 1.15 meters, or this value is, if we express that in megapascals, maybe it's better to express it in kilopascals. So that would be 150 kilonewton per meter square times A. So that would be 1.15 meters square. Just to set that a sense for the values. I always teach my students in whichever course I give that it is very important to get a sense for the values. So if we multiply 150 times 1.15, we will get ultimately a force of 115 times 1.15, we will get a force of 130, so approximately 130 kilonewtons. This gives us a sense how much shear this wall can take in a very simple way. And just to repeat this value of 150, Vm is 1.3 megapascal or 300 kilonewtons per meter square. So you'll have to write this if you want to keep. I can keep it as a slide. And if we divide, then if you divide 300 by 2, you will get this value of 150. Okay, and then you will then that is that force. So I will now go back to presentation mode. So here, let me go back and back again. So this is now for shear resistance of a single wall. Let's say we found out that for, and please note that in this equation, this length L also includes tie columns. Now you can also say, well, but then these tie columns are made of concrete. How can we take masonry? It is okay. You see, we are on the safe side because we are giving them properties of masonry instead of concrete. So masonry has the smaller properties, smaller values than concrete, so that way it is okay. Now here is the next. So from that, we want to derive what is the wall index for a specific building. So at the base of the building, VB, that is the force that we get from calculations of IS 1893, is equal to Vx. So we, instead of Vx, we put VB. And VB is equal to AH, and AH is seismic coefficient, and I'm not going to go over it since you're going to go over it in the afternoon with Professor Chadania Sangui. And then WT is seismic weight. So that is how this is determined, and it depends on the seismic zone of India, on the type of soil, and so on. So different AH values will be there. WT is self-weight of the structure, and in this calculation we assume that the weight is equal to number of floors times the average weight per floor and times the floor area, because weight per floor times the floor area is equal to weight, a part of the weight that is at each floor level. So you have 5 floor levels, you will have 5 different weights, but we take some average weight which depend on the thickness of the floor slab and all that. You have a more detailed explanation in chapter 7. And based on that, we can calculate that WI, or wall index per floor, is equal to 1.5 times AH, which is seismic coefficient obtained from IS 1893 calculations, times W, which is assumed weight of the floor depending on the wall thickness, of the floor thickness, and it's a reinforced concrete floor. It's not the same if you have 10 centimeter thick slab or 20 centimeter thick slab, and then divided by VR over gamma m. So this is all actually derived from this equation, which is framed in red. So if we put on the right actually on the top equation, VR is greater or equal than 1.5 VB. So if we import VB into the right-hand side and on the left-hand side, and also use the fact that you have N times W times AP, substitute that would be on one. And on the left-hand side, we use the fact that we have sum of all wall areas, because again, if we have, and I will now again use that same page to annotate, we have 3 walls. We have areas 1, A2, and A3. These are cross-sectional areas. So then VR for these walls would be equal to it would be equal to VR small divided by this gamma value. Times area of A1 plus A2 plus A3. But because these areas A1 and A2 and A3 is equal to AW. A1 plus A2 plus A3 is equal to AW. That is what we had at the beginning of the section. So if you look at this slide, we said that we are taking AW as the sum of all walls in one direction. Okay, so we are there. And then don't forget that this AP is the plan area of the floor plan area at that level. Therefore, our area is equal to VR is equal to again VR times gamma m, and then times AW. So that is how that was derived. See? So that is that VR, and this VR is capital, so that is with small letters. I can share also this annotated slide with you. So anyways, that is what it is. And then in that equation, which is shown here, we have AP, which is again which is shown in the which is a part of this WT equation, and therefore WT is on the right hand side, VR is on the left hand side. And if we divide AW from the left-hand side over AP on the right-hand side, then we get wall index per floor. So in other words, if we said that this value VR over gamma m is 0.15 in megapascals or 150 in kilonewtons per meter square, we can now see some simple values, and assumptions we will see. Then we don't need to calculate this. You will need to calculate it for your assignment. So in the code gives a table in which you can which gives you wall indexes for floor for different seismic zones. It is in Annex C of the code. I will show you that Annex C. And it says that if it is in zone 3, that is 1.1%. In zone 4, it is 1.6%. In zone 5, it is 2.4%. In the book by which I co-authored with Professor Mitra in chapter 7, there is a more detailed table which calculates exactly these values from this equation. And it gives you values for depending on the brick compressive strength, assumes mortar type M1, which is 1/6 MSM mortar. And for seismic zone 3, for example, if you have 7.5 MPa bricks, we are getting 1% roughly of wall index per floor. And if you get zone 4, it would be 1.4%. If you go to zone 5, let's say Burj, we have 2.2%, which is really high. But if we are lucky and we are in North India and we have 20 MPa bricks, then in Burj, or in North Indian site with 17, with zone 5, we would have 1.7. So it strongly depends on the brick strength, you can see. So the point in this is that the higher brick strength you have, for the same seismic zone, you need smaller percentage of walls. Does it make sense? I hope yes, because the walls are stronger. You see that in this equation for the strength of the masonry, we said that the strength depends on the shear strength depends on the compressive strength, and compressive strength depends on the strength of bricks and mortar type, as discussed in the previous lecture. So it's all connected. It's all connected. Now, the next and the final equation is that this is not the end. This is giving you wall index per floor. So how is that different for wall index for building? Well, it is different in the sense that you need to multiply wall index for building as the number of stories times the wall index per floor. So for this hostel at IIT Gandhinagar campus, which is G+3 or has 4 floors, so we count the number of 4 slabs or roof slabs, 4 levels. That means 4 times 0.01. Therefore, it means that at the base of this building, we needed to have 4% of the walls in each direction. So this needs to be done in each direction. It's not only for one direction seismic loading. So that is interesting, and that is for zone 3, and this is it for Gujarat, which is seismic zone 3. And that is more or less what does exist there. And assigned reading is chapter 7, and I will go over before we go. So that is the end of this lecture, but I want to go before getting your questions. I will then go over Annex C, just to show you in the code. And then we'll have a question and answer, and then we'll go over the assignment, I hope that is okay. So I will just go to I'll keep this. I will open the code. Okay, it's not here, so I'll just open it somewhere else. Okay, got it. Confined masonry code here. I had it all set on my iPad, but doesn't always work. So in the code, at the end, there is annexes A, B, and C. Annex C is I just want to show you what Annex A is, just giving a list of codes. Annex B is what we discussed. It is, we covered that is a determination of shear strength by this diagonal testing. And Annex C is the simplified method. So you can see here exactly what I was talking to you. These are exactly the same equation. And it is showing here this equation of wall index per floor. The equation is there, but derivation is not there. So what I like to do, I wanted to explain you the basis for this. And this table is applicable only for those low-rise buildings. You remember I mentioned that at the beginning, I'll go there, only if they're small buildings, G+1, and it cannot be used for all buildings. So for like hostel type building, you would need to go by this calculation of WI per floor, which is okay, I believe. And here is AH coefficient, which is, as I said, from 1893 is also listed. So, and it says also that WI required is greater than or equal to n times WI per floor, and WI per floor is calculated from this equation. So I believe that is the same, and this can be applied to seismic zones of India 3, 4, or 5. And so that is all regarding this simplified method. The purpose of this lecture is to do two things, actually. Maybe many of these things are just a reminder for you if you are already knowledgeable or familiar with it. But I would like you to take away two things. One is obviously these equations and the way the equations are derived. And the second thing is that this approach can help you to calculate by hand stiffnesses and forces in the walls. In your assignment, you will also need to use these equations, because I expect you to be able to determine forces in individual walls by hand by calculating these proportional stiffnesses based on if you know the total force at a certain level, let's say ground floor level, you can determine the force in individual walls from the equation, assuming that the rigid diaphragm option and the stiffness in the walls, that the wall force is proportional to the stiffnesses. And as I said, since we are dealing with low-rise buildings, it's perfectly fine to say the stiffness is proportional to the area. So therefore, force in the wall will be proportional to the area, cross-sectional area of that wall relative to the other walls. So anyways, this is the end of this lecture. I would like to invite your questions, and then we'll go over the assignment as well. Any questions? I'll stop sharing actually so that I can see you. Any questions? Is this clear? Is this? I'm sorry for having to delay. I really love to use my iPad. I can annotate easily, and I try to do it now by typing, but it's not the same. Is this method new to you? Like, what do you think about it? Does it make sense? Even some opinions are good. You don't need to have a specific questions. The method is used from Latin American countries also. It has been used there, and it is part of the code in Mexico and other countries as well. And as I said, wall index has been used as a parameter after the earthquakes. They have to look at the buildings and find out wall index, because it's not something you can see by looking at the buildings. You need to measure the walls, isn't it? So it's a tedious process, but it's very worthwhile because you can get a sense for your region. What is the wall index for the type of masonry construction you have that is needed to avoid the damage at a specific earthquake? Any questions? So I would suggest that you read chapter 7. Chapter 7 consists in the book. It gives example of two buildings that are, and it goes through just this wall index calculations. It doesn't go through these technical calculations of the strengths and all that. But it is very useful for, I would say, architects, for preliminary design, and for engineers as well, to get a sense. So if you don't have a questions, I will go over the assignment then. Is that okay, Chaitanya? Are you there? I'm not sure how much time we have. You can ask questions also later, but I'm sure you will have questions when you come to assignment. Should they go?
Yeah, if participants, please, if you have any questions, you can ask. Otherwise, we'll go for the assignment. Any questions? No. Okay.
So then
no questions. I guess there are no questions. Yes, sir. Yes, sir.
I can go to the assignment then, okay? I share the screen. You can see my screen, right? I'll save this. Okay. So I will go to look at the assignment, which is, I believe, Professor Chaitanya Sangvi has shared it with you by now. So it is simple assignment. We actually initially wanted to give you
shared.
a project.
It is shared in the WhatsApp group. Yeah.
In WhatsApp group. So anyways, if you haven't seen it, we'll go over it and then you can look at it later. So it is a G+1 building, a low-rise building in this case, but I just want to say that whatever we apply with this assignment, it could be used in taller buildings. I think for the sake of your convenience, it is a lower-rise building that was chosen. We initially wanted to do a project of a hostel building, but it was given up because of the nature of the course online. But if it was offline, it would be an online. So it is an bungalow building with a certain number of, in fact, it's very similar to the one that you have in the chapter 7 of the book, but it gives some dimensions of the walls. So you have walls in both directions. They're intended to be confined masonry. It doesn't show right now any confining elements, so it's up to you. It will be part of your task to determine the locations of confining elements as one part, but the dimensions, lengths of the walls are given. So that is, and the dimension of the plan and all that. So it is G+1 bungalow, very common to, I would say, Ahmedabad. I lived in bungalow like that for some time in Chankeda when I was initially working at IIT Gandhinagar. So consider a G+1 bungalow, but it is located in Bhuj, Gujarat. And it has clear floor height of 3 meters. The bungalow has confined masonry walls and reinforced concrete floor and roof. Brick masonry wall thickness is 23 centimeters, and the floor roof slab is 10 centimeters thick. The floor is assumed to act as a rigid diaphragm. First, you will need to use the knowledge from the afternoon, calculate the base shear force for the building according to IS 1893 standard, and find the distribution along the building height at each floor level. Draw shear force diagram for the building showing story shear forces. That is very simple, and it is all based on the afternoon lecture or your knowledge already from the IS 1893. It's nothing specific. In the IS 193, and Professor Chaitanya will talk about that, is that you need to find, to use the R factor for confined masonry, obviously, in this case. Then the second part is find the seismic shear force in wall X8 at the ground floor level by hand calculations. So wall X8 is this one. You can see it here on the top in the middle. It is in vertical direction, and that is the wall. It is about 4 meters long. So then you need to identify the walls that could be treated as confined masonry walls in this building. You need to draw on a diagram where the tie columns. Please note that based on our discussions yesterday, not all walls will be considered as confined masonry walls. It depends on the openings and whether you have confinement around the openings or not. So that will depend. That will make. So you have to look at a case-by-case basis. It's not a generic decision. It's different. That makes a difference between that and the reinforced concrete frame system. Then the next step is again something you could do based on today's lecture on calculate wall index in X and Y directions, and check whether the wall index is sufficient according to the draft IS code requirement. And if it is not, I would say that you would need to modify right here at point D. If it is not, you can choose thicker walls. The walls are recommended to you to be 23 centimeters. If they need to be thicker, you can take thicker walls. But what is important, you can dream, instead of choosing thicker walls, you can change the assumed property of bricks and mortar. So you can choose the required properties so that this meets your requirement, because you will have to assume in choosing this wall index according to the code, required wall index, you will have to assume already brick and mortar. So that is going to give you a sense what do you need in terms of masonry properties if you want to make this work. Frankly speaking, and I believe that you agree with me that for G+1 building, 23 centimeter thick walls should be okay. Why would you choose thicker than that? Then the next thing is to design confined at part E, you will be able to do on Thursday. Design confined masonry wall X8 for the combined effect of gravity and seismic loads according to a draft Indian code. Check resistance for shear and axial load and bending according to that code. And we will use limit states design approach. As I said, it could be done otherwise, but with allowable stress, but not done. And last but not least, I know you are all interested in doing the modeling in SAP 2000. You are also asked to develop a model of the building in SAP 2000 using the wide column modeling approach, which we will study tomorrow. And tomorrow we will also go through the use of SAP 2000. So you can model it in SAP 2000, and you will be asked to apply seismic force again in X direction only, and you can check for the walls if you have X8 or any other wall, you can compare it for X8, definitely you will do by hand calcs. How does it compare to what you have got through by hand calculations? I told you here to assume 10 MPa bricks in the assignment, but you don't have to. You can go, that is maybe initial assumption, just to give you some starting point. You can change the strength of the bricks as needed to make this work. So type H mortar I would keep. I would suggest to use the strongest possible mortar, but you can go with the higher brick strength if you need. Weight density of bricks is 19, that is true. Weight density of concrete 24, and assume typical window height of 1 meter and door height of 2.1 meters, because you have doors and windows. You will need to take them into account in your model. So that is all for the assignment. In fact, it's not very elaborate, but I feel in addition to the quiz that you will get on Friday, that it is really necessary to do a hands-on design for any design course, including this one, even though it is short and it is online. But we feel that it is possible to do it and submit it. I believe Professor Chaitanya will set the submission date. It may not be necessarily the end of the course, but it will be really important that you do this assignment. So I will stop the presentation, and then maybe there are some questions now, or maybe not yet, for the assignment. Any questions? So this is really, yes, go ahead, please.
Yeah, no. I'm just asking faculty members to ask questions if they have. Yogesh, yes, please go ahead.
Okay. Can we apply strut and tie theory to analyze the confined machinery?
Yes, we will talk about different models tomorrow, but I'm suggesting to use wide column model. Strut and tie model is okay, but it's really elaborate, and you would never use it for a design of a bungalow. You would not use it for most buildings. It really requires much more effort for analysis. I would suggest that if you want to use strut and tie, you can use both strut and tie and wide column as a better exercise. White column is the standard method used for design of masonry, confined masonry buildings. It could be also, they could be also used as a wall systems. In fact, there were some, and I will share with you some papers showing that as an option. Okay, so I will share tomorrow because we have that lecture about modeling. So then I will share both about white column and strut and tie. You can use, I would personally not recommend, this is initial example for you. You have never used white column model either. So that is going to be complex enough for most of you. Because if I'm correct, most of your education was based on the frame systems. So this white column model is going to be new to you because of the transform section properties that you need to use. Strat and tie method would be even more complex, and it requires the knowledge of limit analysis, which is not limit states analysis. So it is completely different approach to design. So the approach to design with strat and tie model would be different from design according to what we are doing according to a code, but in the code it is allowed as an alternative method, but it does not give any further guidance. So tomorrow we'll talk both about, that is my lecture for tomorrow, modeling approaches. My suggestion is just for consistency of the whole class to use white column model, but if some students want to do strat and tie, they can do strat and tie in addition, but it requires modeling in SAP 2000 in any case. And you need to determine properties of strats, properties of ties, and they're different for every single element. And for the walls, it's slightly easier to determine for white column. It's less work for you to do, because if you could see, you have at least 8 or 10 walls in one direction, which means that you need to determine 10 different properties. Every wall has different length, and so the properties of each wall will be different for the model. So it will take, I would say, fair amount of time. Of course, any time is okay, but if you want, you can do both methods, but white column model is mandatory. I recommend it for this assignment, let's put it that way, not mandatory. But if you want to do more, that's good for you. For practice, for learning and practice. Strat and tie model is not convenient, conventional use for confined masonry. It is a research topic, I would say, right now. And I share a research paper by one of my former students, and which was published recently in the strat and tie model. And actually, few research papers have been published at IIT Gandhinagar and IIT Patna and all that. But it's not, I wouldn't say it's most friendly method for conventional applications. And what I would like you to, since this is an initial course on confined masonry, I would like you to know the basics, and then you go from there. But if you wish, I'm more than supportive to do other things and more than basics. Go ahead, please. Prakash and somebody else. Go ahead, please. Question? Are you muted? Can you ask questions? Prakash? His hand, but no question. Can you maybe ask him to unmute, or? Not sure.
He is unmuted, ma'am, actually.
Okay. Okay. But he's not asking question. Prakash, do you have still a question, or maybe you gave up?
If any other participant also is willing to ask the question regarding this session or the previous session as well, if you could not have asked in the previous session, or regarding the assignment which ma'am explained, please you can ask now.
You will be also able to ask, you're most welcome to ask tomorrow as well, because today you will have opportunity to read by yourself, and it takes some time to digest and all that. It's not complicated, but still. And so tomorrow we have a lecture in the morning. We can discuss that as well. As I said, this last part, the modeling part, is coming extra, so you can solve all the other parts without any sub-analysis. And in fact, if you ask for my opinion, I would always do this by hand. And even if I do sub-analysis, I would still do analysis by hand, because only by hand I can tell what I'm expecting to get. So I hope, and one of the big things that we need to achieve in the engineering education is to prevent engineers who are doing black box approach with garbage in, garbage out. So hand calculations and approaches for checking the results of computer analysis are critical. So in any case, even it was a 10-story building, I would have done a hand check to do it. And I always request it from my students when they do projects. So this fact that you are doing everything by hand up to the last part is very typical for any of my assignments or projects, at least that I practice anywhere that I teach. Prakash, are you able to or willing to ask question? You can also send the question by email. Chaitanya, I don't mind if students have my email. I'll share maybe by email at UBC, which is I have at IIT-GIAN, but I'm not checking that one regularly. So I can give, if you wish, please give to the students my email at UBC. I will share with you. I think you have it, but just in case, you can share it through WhatsApp, and they can contact me by email as well.
Okay. Yeah.
Hmm?
Yes. Okay.
So if there are no questions, I believe that is fine, because students can read, digest this material, and I strongly suggest to read chapter 7. That would be useful. As I said, this simplified approach, there are no papers in India, published papers so far about simplified approach. There are some papers in English language, but they're not exactly the same as this one that was proposed here. And so this derivation that I shared with you is the only one that currently exists, I would say, that explains how this has been arrived at. So I hope that in future there will be engineering guidelines for engineers, which would include this and other examples of application of simplified approach, examples of design. We started that at IIT Gandhinagar, but stopped the project of developing the guidelines. Maybe the project will continue now that the code is on, but I'm not sure right now. So that is the situation, I hope. Or maybe if it is not at IIT Gandhinagar, there are other IITs which have active research in confined masonry, such as IIT Patna and IIT Guwahati, Professor Heman Kaushik and Vaibhav Singhal. So maybe they will move forward. They're younger and have more energy to doing that. So anyways, that is all. Any questions?
Yeah, Ronak is there.
Yes, sir.
Ronak? Yeah,
Good
please.
morning. I'm Ronak.
Hello.
I hope you remember we had a session.
Yes, I remember. Yes, good to see you.
Thank you, ma'am. Ma'am, I have one question which is not exactly related to confined masonry, but you somewhere discuss about the prism test and that test to be performed on the brick masonry. Ma'am, I have one doubt that the majority of the condition assessment that is being done in the consulting work that we seen in around our country, when we talk about condition assessment of the building, we hardly see any report doing the prism test. They just do NDT test, that is rebound and UPV test on the slabs, and then the results are out. The main problem of doing the prism test on the site is that we have to have that cutout, and then the person are not very much willing to have that cutout in their walls, and the client is also not very eager for that 3 sample test that needs to be performed. Ma'am, is there any alternate way entity test that prism test on site can be recorded? We need to cut that prism. But
That's right.
then we have different buildings, and that time required, the cost required, and the practicality of getting prism from many of the places are not possible. And then half of the part of the masonry goes like in the assumption only that no reports, no test on the NDT, just the reports on the slab that is concrete. And then what is masonry? The suggestions come that the box section is not there, this is not there, but there's no, it's actually a black box. What is the existing strength of a mortar, or what is the existing strength of the brick?
Yes, which is critical for that structure rather
Yes.
than concrete. So there are several ways. Yeah, I agree that this is difficult to cut. I think it's not practical to cut a prism. So one way is that to test bricks only, and to take bricks from some site location where it is not critical, let's say basement or somewhere where you can easily, or somewhere in the window area where you can, remove, okay, it requires some distraction. So brick strength, if it is brick masonry, brick strength tells us a lot. So even if even if you you're not able, you don't have enough bricks to do a prism test, that is enough. Secondly, I would suggest, recently, a few years ago, New Zealanders have come up with a scratch test. Which is very good field test, and there was a PhD thesis of someone, and they applied it in Nepal, and it is a part of New Zealand official guidelines for assessment of masonry structures, which is available, by the way, free of charge in New Zealand, but you need to find it. I can share a link, and I would suggest that test, because you see, this scratch test is related to toughness, and toughness is related to strength. So in the absence of ability to do the proper NDT, test, which would require removal of brick and then and finding the stresses, that is, to me, everything is better than no information.
Yeah.
But strength of bricks, if you take strength of bricks, and then even from the code, as Professor Poonam was saying, maybe that is not that good, but still you assume some lower strength of mortar if it is old masonry, then you already get some sense of it. But the key piece of information is strength of bricks. If you get a sense how strong are the bricks, we know that mortar is weak. So we can assume weakest possible mortar, and then you get some strength, a sense of F prime M or allowable stress, whatever you need. So find, at least in the project that I worked on, always find some locations where you can access bricks, and there are some loose bricks that could be removed in older masonry that is possible, and maybe even, they wouldn't be returned because they would be destructively tested, but that it would require destructive test. They can be replaced by some other bricks anyways, or something. If it is a heritage building, then still there is a basement which is not heritage, so you can do it there. So, but I can share, if you are interested, you can send me an email. I'm not sure if it is of interest to the entire group, but if you're interested, it's excellent publication. That test is very well documented. Basically, they have different nails with different size of nails, and they specify exactly what kind of scratch is required and what is the result expected of that. So it's perfectly documented, and it has been extensively studied. Somebody has done PhD on actually that topic in New Zealand.
That's great.
So it doesn't cost anything. It doesn't cost anything, and it is not destructive even.
Yeah, it's very much helpful for the basic assessment, definitely.
So I will share now my email, just in case, with Professor Chaitanya. He will share by WhatsApp. So send me an email, and I will send you a link to that. Maybe it's best if I send you a link to that page where this code is posted, and then you can access it anytime rather than me sending you the documents. And I can tell you which section it is and all that. So yeah, very good question. Yeah, I've seen in many countries. I'm working a lot for World Bank projects in Central Asia. Same story. They just don't remove, and they just test concrete in a masonry building, and they don't have any values for masonry. That is very common in other countries too. Unfortunately.
Thank you.
Yeah, you're welcome. So I guess this is the end of our session. You need some break and lunch in your case, and I need breakfast. So I think you can. I think Chaitanya, this is the end of our session for me for today. And next session is yours, I believe, for IS 1893, very important one. And do you want to say when you're resuming the activities? Hello, Chaitanya.
Yes, ma'am. Yes, ma'am.
Or yes, you're going to say.
Yes, ma'am. Thank you. Thank you so much once again for this couple of amazing sessions. Quite informative and explanatory. And I can speak for the participants that they could have easily grasped all the details which you explained quite meticulously. So thank you for these sessions. And not to mention once again that you had to wake up so early in the morning for these sessions. And
That's okay. I have a longer day.
thank you, ma'am. So that would be the end of the second session.